Okay, let's get started. Um, Changing back to twisted magic angle graphene again. Last time I showed you some movies and fun stuff. Today I want to get back to trying to be a little bit more concrete about explain a little bit how you actually obtain some sort of model for these flat bands in twisted bilayer graphene. So at least that will be at least the first thing we do today. Hopefully not the only thing we do today. And then we'll go on to talk about the many body physics. And it's buzzing somewhere. Maybe it's my phone. Yeah. This is what people do in talk shows. They run through the audience, right? Come on. Sorry? Yeah. It'd be pretty good if I arranged that in advance. Okay. This was actually done well before any of this magic angle experiments, in some beautiful theoretical work I mentioned by Bistreitzer and McDonald in 2011. So I'm going to explain what this continuum model is. I gave the reference the last time. It'll be easy to find. Just Google it. This model kind of accomplishes a few things. It shows how to recover an actual model that obeys Bloch's theorem, actual periodic model for arbitrary twist theta, indeed then gives a way to do calculations, without 10 to the 5 atoms in it. And it elegantly, what I particularly like is it elegantly reduces or exposes the important dimensionless parameter. Okay. Bistreitzer McDonald derived this in a particular way, which is fine. It's a bit technical, I would say. I mean, it's not technical in the sense of like really fancy theory like gauge theory. Okay, no gauge theory today, I think. But I find it very mechanical. What they're doing, it's not so obvious how to get insight. Just explain in words what they do. They take the conventional description of single layer graphene and some lattice, but allow the lattice to be rotated, the two lattices to be rotated, and then they explicitly try to find the overlap in a given between a given wave function in one layer and another by taking into account the real space positions of all the carbon atoms in one layer, all the carbon atoms in the other, the wave function in the local frame, and then multiplying those wave functions and summing them over the lattice, and doing that, re-expressing this using basically Poisson resummation formula in a summation over wave vectors, and then doing kind of manipulation that theorists like to do with these Poisson resummation formulas. It's all kind of technical. At the end, something nice comes out. The whole discussion is done in momentum space. The funny thing is the thing is much simpler in the end in real space. In the end, you could almost guess what the result is, and so it'd be kind of nice to have a derivation that doesn't go through this kind of indirect route. And I wish I could say I had a perfect derivation. I don't, but I have something like a derivation, so I'll give you that, all right? And you can always look at their paper and many others like it that have made small refinements if you prefer that, okay? So that the picture I want you to have in mind, so this will be let's put derivation in quotes. Is really based on the images that you saw in my talk or in Dima's talks last week, that for a small twist angle, the Moire pattern really looks locally like just like a uniformly translated pattern. So if I don't twist two layers and I just translate them, I can make different types of layers. I can make this AB, BA, AA, or I can make something in between. You saw that I could turn AB into BA by translating one layer vertically by one carbon-carbon spacing. But if I go halfway, I get something else. Now that's still a translationally invariant pattern, it's just a lower symmetry pattern. Everywhere in the Moire lattice, in the twisted system, it looks approximately like one of those patterns. If you looked at that Moire structure, you would see somewhere, you'd see a triangular lattice of AA regions, something like this. And then, now do I really know how to do this? In between here, you'd see AB and BA regions, probably something like this. I don't know, AB, BA, I forget, and they kind of alternate. Okay, something like this. Don't take this too seriously. You can look, there's nice pictures in many of the experimental papers of this. But the point is that everywhere locally, if I look, this is a huge length scale, you know, many, many, many carbon spacings for these 1 degree twists. So these are almost uniform regions. So what you can sort of think is that somehow I should be able to write a Hamiltonian which is just a slowly varying function of space. So our problem right now, this continuum model is a 1 electron model. So we're trying to write a Schrodinger equation. You know, what you would seek is some Hamiltonian, which is a function of position, you know, which looks like the AB Hamiltonian if X is in a AB region. It looks like the AA Hamiltonian if X is in an AA region, et cetera. Okay. So that is somehow what intuitively we'd like to have. How could we get there? All right. So we can get there by this Bistritzer-McDonald route. But another way to get there is to think, as I just mentioned, any of these regions can be obtained from any other. Let's say the AA region, we can convert it to AB by just translating it. Okay. In fact, you know, if we translate AA, let's say up, we'll turn it into AB. If we translate it down, we'll turn it into BA. Okay. So we can view all local regions are just basically translations of AA untwisted bilayer graphene, no T. Okay. Now, of course, we can't reproduce the Moire pattern by a uniform translation. We need sort of a non-uniform translation. So that a non-uniform translation is just a strain. Okay. You can think of twisted bilayer graphene, at least for small angles. All this is small angles. Is just some system with a non-uniform strain. Okay, technically it's mostly shear strain, because you can think of the two layers as being strained differently. That's what the rotation is. Okay. So in fact, there's a well-known result from elasticity. How many of you had elasticity in class? A few, yeah. Colin, the old farts said this, but I'm not sure they teach it all that much anymore. Oh, you too? Yeah. Yeah. So I'm all the youngsters in the back row, obviously. Yeah, okay. I thought it was a big deal somehow when I was in school. Good. So this, basically, So if you haven't had elasticity, you probably, hopefully, you know a few facts from it. You know, a solid, any solid has some elasticity. There's around its equilibrium state. There's some energy cost for compressing it, for stretching it, for shearing it. One of the things you learn in the theory of elasticity is there's no cost for rotating it. Okay, because of course I just turn the block of a crystal in free space. It doesn't cost any energy. And so one of the basic results of elasticity is that a certain small, so usually we form elasticity is phrased in terms of what you might call displacement field. Some vector u of x, okay? It tells you, you know, the conventional story is that the coordinate of an atom which in equilibrium was at position r is shifted by some displacement u of r. Okay, this is what you learn in textbook Ashcroft and Merman or something. If I look at, let me focus on 2 dimensions because it's simpler. Okay, in 2D there's only one way to rotate a sample. Okay, rotate in the plane. There's an expression for the rotation angle, which is 1/2 dx uy minus dy ux. Okay, so that's kind of easy to see if you want to twist. Let's say you make a small rotation. Under rotation, you know, x goes to x minus theta y, and y goes to y plus theta x. That's expansion of a rotation for small theta. Yeah?
Okay, just so I understand what this displacement field is. It's a mapping, so it exists for all points in your space.
Yes.
And it's a mapping from an old coordinate system to a new coordinate system.
Sure, yeah.
Okay, so say we have...
I've got to get to, there is some subtlety maybe you're trying to get at eventually, but let me not get to it. Go finish your statement.
So say we have like some trampoline sheet, right? And it's flat. Okay, and then we pick it up and we can stretch it.
Yeah, so far what I'm telling you is nothing to do with any vertical displacements, okay? Just in the plane, like some rubber sheet, I could pull it a little bit this way. Or,
so
yeah.
if we get some chalk, can we draw on this sheet?
Mm-hmm.
Okay.
Yeah.
And then if we put it on the ground, this sheet is big R.
Yeah.
And then when we can, you know, pull it and stretch it in any way in the plane, and then this gives us the
Little r.
U, and then this maps big R to little r.
Yeah, little r is I mean, the way you can think about it like that, exactly, yeah. I mean, for here, if we talk about crystals, which is, you know, graphene's a crystal, so you can just think about big R as the positions of the carbon atoms in the undistorted structure.
Okay.
Okay? And now I distort it a little bit. I pull it on it like this. Little r is the position of the same atom which used to sit at big R in the distorted structure. Okay? I will raise a subtlety with this in a moment, but not immediately. Okay? Yeah. And so if you look at, for example, Landau and Lifshitz' book on elasticity, he will tell you that this theta corresponds to a global rotation of the lattice. And so for an isolated solid, a 2D solid, you can, in general, in 3 dimensions, you know, this is a 3-component vector, and you can write 3 of these things, which are antisymmetric combinations of U. And those cannot enter elasticity of a 3-dimensional solid, because a solid is invariant under a rigid body rotation. So usually, in elasticity, you learn that the strain tensor, epsilon mu nu, which is the only thing that an ordinary solid's energy can depend on, is a symmetric combination. Okay. So this can include shear strains or dilations, things like that. Okay. And you know, strictly speaking, for the bilayer graphene, it's still sort of true, except there's a sort of shear which corresponds to a relative rotation of each layer. And that's actually the most important thing for us. Okay. So what I'd like to do is, it maybe sounds a little ambitious, let's write down a general Hamiltonian for bilayer graphene for any strain, any independent strain in each of the 2 layers, including rotation. and then specialize to the case where the only strain is a rigid rotation of the two layers, and opposite rotation of the two layers. Okay. What I'll write down at first is, more or less completely general. Okay. But yeah, so you could, but we don't need to do that. I mean, that's yeah, that's the idea. So, in fact, so this continuum model of that Bistreitzer and McDonald did. Apparently, my iPad can't recognize me with these with this thing on. So it turns out you can obtain basically the Bistreitzer-McDonald model by starting with just a model for bilayer graphene with strain and specializing to a strain which corresponds to a shear rotation. Okay. So that's the procedure. Okay, and we're gonna ask, how is not twisted bilayer graphene, but just bilayer graphene affected by strain? So there are three effects, sort of three categories of effects. All right. So one effect, in a way, is trivial, but it'll be sort of important, is pure geometry. So these are effects of each layer. Okay. So, if you strain a sheet of graphene, you're changing things. You change the distances between carbon atoms, the relative distances, you change angles. These are physical effects. The hopping between two carbon atoms changes a little bit. Okay. The local environment of a carbon atom changes its symmetry a little bit. So those are physical effects. There's just purely geometrical effects, which is that the position of the carbon atoms move. And that's just, in the sense, as a theorist, we can separate the physical effects from just geometrical effects. Suppose that none of these physical properties change. The hopping between neighboring carbon atoms stayed the same. The local symmetry of a carbon atom stayed the same. The energies of the carbon atoms stayed the same. Then nothing would change in the reference frame of each carbon atom. But because the carbon atoms move and we observe it in the lab frame, things will look different. Okay. So the most obvious thing that changes, for example, is that the K points move. Okay, so if you took a single layer of carbon, you take our graphene lattice like this, our rubber sheet, and I pull it like this. Typically it would compress a little bit like this. This is real space, this is K space. This, measured in the lab frame, these K points would move out a little bit. Okay, there'd be a different momentum for the Brillouin zone corners. Okay, there will also be physical effects that this hopping will now be different from this one. Yeah. Yeah, at the moment, yes. So this, we'll make it local, okay? So that the assumption is going to be, we want to consider a strain that's slowly varying. Okay, which is true for twisted bilayer graphene. So we often do this in physics. We expand physical properties like free energies or equations of motion, different quantities we're interested in. We expand them in powers of things that are small. Like in Landau theory, we expand in powers of a small order parameter. We also expand in small gradients. Navier-Stokes equation for fluids is kind of an expansion in gradients of the velocity of the fluid, for example. Okay, we're going to do that type of thing. It'll be a little bit important. We'll worry about how to take it into account. Okay, that doesn't fall into this category. All right. There's a second category of effect, which is actually, changes of each layer's energetics. So this is the other type of effect I mentioned, that the bond length changes, that changes the hopping. Okay, that's the most important physical effect of straining a layer. Okay, the different bonds. For example, if we did this, we wouldn't be stretching these bonds very much, but we'd be stretching these somewhat. Okay. So the simplest type binding model, you would say, well, now this hopping is different from this hopping. We'd have a T here and a T tilde here. Okay. And they differ by an amount proportional to the strain, generally. Okay. So this is something that's been studied a lot, much more than this. Normally you don't care about this. It's not actually changing the physics of the layer very much. We care about it mostly if we actually strain the two layers differently, and then their relative geometry starts to matter. Okay. Here, this has been studied a lot, and in graphene, the main effect is what people call artificial gauge fields. Sorry, gauge fields. God damn it. But we're not going to consider them. That's the good news. I just have to mention them. How many of you heard about artificial gauge fields in graphene? Yeah, sure. All right. The good news is they don't matter for us, okay? These are actually less important than there'll be three effects, and this is the least important effect, okay? It has some role, but not much, okay? So from here on, I'm going to forget about it, okay? The basic reason is these so-called artificial gauge fields are actually proportional to the strain tensor, which actually vanishes for rigid rotations, okay? Finally, we have stupid thing I need to get. This is annoying. Oh, there we go. It recognized me that time. Is changes to the interlayer coupling. So this is really important because, locally, if the two lattices are displaced differently, they have completely different tunneling between them. We saw that the AB or BA graphene has a completely different electronic structure than AA graphene. So this is probably the most important effect, okay? We're going to need to take into account these two. Okay, so let me talk about both of these in turn, all right? So let's talk about these geometrical effects. Okay, so now I have to actually get back to your question a bit about what this displacement field really means. So we're going to talk about one layer here, okay? Each layer separately. Everything I say here we should apply independently to the two layers, and at this point we can imagine each layer is strained however we want, totally independently, not necessarily rotated, anything else. So the textbook way, to describe a strain, by textbook I mean if you look at the theory, let's say example, phonons in Ashcroft and Mermin, that's how they will do it, okay? Ashcroft and Mermin will tell you the position of the atom, which in the equilibrium structure is at R, is now at X, which is R plus U of R, and U of R is small compared to R. Okay. So this is an example of what are called Lagrangian coordinates. How many of you had fluid mechanics? It's slightly more than elasticity, right? The Europeans like fluid mechanics. Good for you. Americans hardly ever get it, which is a pity. Lagrangian coordinates in fluid mechanics means there are coordinates that are identified with a particle. Okay, so the coordinate R here is the location that an atom had in the undistorted structure. So usually for elasticity theory, the assumption we need to have normally is actually not that U is small, but that the relative displacements of U of nearby atoms is small, because all the energetics of the solid just depend on the relative displacement of the atoms. So, and in fact, in a twisted structure, to describe a rotated structure, U will get large. Okay, because you go far away, at the displacement, if I rotate around here, an atom somewhere along the position of my arm will move to here. Now, if I go far enough down my arm, even if the atom is small, it will have moved by a large distance. However, the relative displacements will still be small if the angle is small between two atoms. Okay. So the problem with Lagrangian coordinates is that in Lagrangian coordinates, actually, big R is no longer the position of space where the atoms are residing under such situations. Okay. The fluid mechanicians have a solution to that. It's called Eulerian coordinates. The idea is to label the displacement, in that case of the fluid, but we can do it for a solid equally well, of the atoms not by where they were in the undistorted structure, but by where they are in the final structure. Okay. It looks a little weird, all right, because this is actually an implicit equation for x, all right. But for example, you can obtain this by iteratively solving this equation, all right. Solving this equation iteratively in U. For small u, you can just iteratively solve this, okay, and you can use this, okay. And this is beneficial, it'll be very important for us. Why? Because we want to describe locally the properties of our graphene sheet at some fixed position in real space, because what we need to know is we want to describe how do electrons tunnel from one sheet to another at the same coordinate in the xy plane. Okay, that's where they'll tunnel. They won't tunnel at the same original position of the layers. Okay, does that make sense? Okay. All right, so this is what we really want. All right. For small displacements, these are interchangeable because U is small. If U is small, then X is approximately R. Okay. But when we have a large displacement but a small gradient, it makes a difference. Okay. So now let's try to figure out how to apply this to graphene. Oh, I should tell you this story. You know, this derivation is not. Well, it looks like I wrote le model. Huh? This is not anywhere. Okay, so it's you won't. If you don't follow this, you'll just have to find a different derivation. Sorry. I hope there will be lecture notes. Yeah, I intend to give you something, but you know, do I promise strictly? Yeah. Probably, yeah. Okay, so what do we want? Well, again, so I've tried to hammer this in over and over and over again. All the physics we care about is described by the Dirac model. So we want to understand how are the Dirac fermions affected by these strains, okay? So that's our goal. We need to apply this, see how this displacement field appears in the description of the Dirac fermions. So for that, we can look near one valley, okay? Let's, for example, look at the K valley. Remember what we did before? We said that the position, the electron operator at the position R of a carbon atom. So here we did something for an undistorted graphene layer, so that I'm going to use this notation capital R. The low energy physics came from states near this K valley, and we introduced a Dirac fermion like this, okay? Let me call it psi plus, and then there would have been another psi minus for the other valley, okay? And if you want, you can put spin and sublattice indices and all your favorite things, okay, on there. All right. But now, R should be given by this. So we can solve this for R. It gives x minus u of x. So this is e to the I k dot x times u minus I k dot u of x psi plus at r. Okay. So, this expression has the same form as the expression, so this is kind of expressing it. In principle, I should write r as r of x, okay? Using this to find r of x. This has the same form as this expression, expressing the electron operator in terms of a plane wave component and a slowly varying Dirac field, now in this lab coordinate frame, okay? So just comparing the two, we read off that psi of x, we just call this thing in the bracket psi of x, is e to the minus k dot u of x psi of r, okay, if you want r of x. Right. Okay, so that's important. All right, and of course we can invert it, And again, here should be x of r. Yeah. All right. So this gives us a way to relate the operators in two frames, if you want. Okay. Again, there's no, I'm not changing anything about energetics, just changing coordinates. So let's now ask, again, not changing the energetics, we can write the Hamiltonian for Dirac fermion, all right? For the right-handed one, it looks like this. It's in the original coordinate frame, it had minus IV, psi dagger of r. So this is for the k valley. So there's tau x dx plus tau y dy psi of r. All right. Now we just want to plug in psi of r in terms of psi of x and change variables to x. Okay, that's what we're going to do. I'm not going to do it in gory detail because it's a little bit ugly, all right? So we're going to just stick this formula in here, and then we're going to transform from r to x. For example, d2r is d2x times the Jacobian, usual for coordinate transformations. It's the determinant of that matrix of derivatives. We can also use the chain rule to express, this we should be careful. So this is d by dr x. These are, the original undistorted coordinates. And we should switch them to, maybe this is better if I write it like this, tau mu d by dr mu. Okay. We want to change these r derivatives to x derivatives. D by dr mu equals d by dx mu x nu dx nu dr mu. Okay. All right. And since we know the relation between x and r, and we know the relation between the two sides, we can put this thing in. All right. And if you do it, okay, then I'll just write what happens. All right. We find the following thing. And assume small u, okay? Small gradients of u. Okay. So we find the following thing. Tau mu u mu dx nu. This is going to be hard to read probably. Del dot u tau mu d by dx mu minus v k dot d mu u tau mu psi. Okay. I guess I put a plus. All these things have a plus, right? Because they're the right-hand Dirac point. Okay, hopefully you're not too dazed by the indices. hard to get the red. Come on. Huh? Oh, really? I managed to get something. It's all right. Next time I'll get a new one.
I'm sorry, I'm confused with the Jacobian one.
I evaluated it. Okay. Yeah, I'll point, let me go through one at a time, all right? This term, tau mu, d mu, that's just tau dot gradient. That's the original Dirac term. Okay, so everything we're doing is expansion in small u. So there's a zeroth order term. That's a zeroth order term. This is what would happen if there's no distortion that doesn't involve u. Okay. This term comes from transforming the derivatives. Okay. So this is kind of this is rotation of the gradients. All right, because the original Dirac theory has, tau dot gradient. Rotate or strain in general, these things, not just rotation, strain. Those gradients also transform. Okay. This is a Jacobian. So if you know a little bit about elasticity, the divergence of u is minus the divergence of u is just the fractional compression of the lattice. That's related to, the bulk modulus describes how the energy reacts to such a compression or expansion. Okay. So that's why it appears in the Jacobian, because this is just the area element. So if I compress the lattice a little bit, I change the area. And this comes from actually this transformation here. Okay, this comes from the change of psi. And it corresponds to just geometrical shifts of the Dirac point. Okay, so we can break down all these things. This is just algebra. All right. Okay, so this is all, it's purely geometry. I just made a coordinate change, so no physics has changed at all other than coordinates. All right. This contains this kind of physics that, if I put a uniaxial strain, the Dirac point will move out or in. Yeah, okay. Let me just leave this. What I want to say is actually that some effects are more important than others. In the end, we're going to just be rotating the layers, okay? And so actually there's no compression. This will just vanish. But if we did compress a layer, it would play a role. This has a small role, but not very important. Okay. Bistreitzer and McDonald treat this term, and it makes very small effects compared to this. This is a kind of not that important. I'm going to basically neglect it too. But we can add it in. We can drop it. It makes some effect, but not a huge amount. This is really the important term. Okay. This is the important effect. And this is really simple, this is not rocket science. It's just you stretch the lattice, the K-point moves. Okay. Okay, great. Yeah, so just maybe saying, this means delta K mu is, in general, is plus or minus. Actually, you probably shouldn't trust any of the signs. All right. So if you have a displacement gradient, that this gives a shift of the K point. Okay. That's all that means. All right. So next thing we need to do is consider this third element here, okay? Interlayer coupling. Interlayer tunneling. All right. In general, it's not just interlayer tunneling. There's also interlayer interactions. Because if I have, two shifted graphene sheets, there's also a potential of one sheet on the other. But we know from studies of untwisted bilayers that the tunneling is the biggest effect. So I'm going to not worry about that. Yep?
Just a question. So essentially what you have derived there is precisely what the others called the artificial gauge field, right? I mean, if you had a local strain,
There are more effects in the artificial gauge field. So this you obtain without any changes to the hopping amplitudes. Okay.
yeah.
The usual artificial gauge field expressions involve actually the strain tensor only, the symmetric strain tensor. This involves the full strain, including the rotation, so it is different. It's not very different. There's part of it is contained in that, but they mix up the two things. So there are two effects. One is purely geometrical and one is physical, and this is only the geometrical part.
Derivative, I mean, a correction to the hopping term.
Exactly. It's usually expressed as a derivative of the hopping. Okay? Yeah. But we're going to drop that. All right? Yep.
Why don't you, like in mathematics, include the strain squared terms? A squared, strain squared terms. Those would affect the curves.
So, well, we could. They're smaller. They're second order in the angle. Okay.
Wouldn't you need that to maintain the rotation variance?
There's no gauge symmetry. Yeah. Yeah. Okay. So what I'm going to assume is that we can neglect potential interactions between the layers and just think about interlayer tunneling. So that's what Bistreitzer and McDonald also assume, although it wouldn't be difficult to add those effects in as well. Okay. So what do we seek? Well, we expect this tunneling is local in the lab frame, right? So we're seeking an interaction of the form like this. Now I need to be sort of explicit about the layers. We want to tunnel, let's say, from layer 2 at the right Dirac point. In general, this can depend on the displacements of both the first and the second layer, all right, into, well, in this case, actually tunneling from layer 1 at the K valley into the Dirac point at layer 2. And conventionally, you put a minus sign here. It's not so important. Okay. So you can think about 1 if you want as a lower layer, 2 as the upper layer, right? And there'll be, of course, the conjugate process, all right? Remember, these are Dirac fermions, so this T is a matrix, all right? We're assuming it's spin-independent tunneling, so it's just a matrix in the sublattice space. All right? Now, in general, this matrix may also depend on gradients of U, not just U. It should be a functional of U, but we expect that it's local. Okay? And unlike the first effect, which only depends on gradients, the tunneling depends on the absolute displacement. We know that because AA and AB tunneling is very different. Right? So this is a little tricky. The logic I'm going to follow, which is I'm not entirely happy with. I feel like there's a more elegant way, but I haven't found it yet. So we'll be a little inelegant in order to get an answer. All right, is we're going to first do this in the R frame for small u, uniform u. And then we'll transform to the real frame, okay? Now I think the reason I'm having a hard time making it work otherwise, and I think there's some subtlety with understanding how exactly to do rotational operations on this, in this lab frame, but all right, anyway. So, that's kind of twisted logic, I guess it's appropriate to use twisted logic for this problem. Okay. Now what do we know about this tunneling matrix? Well, it's very strongly constrained by symmetry. In fact, it's almost completely constrained by symmetry. So first of all, let me just tell you what the symmetry constraints are. One obvious constraint is that if I translate both layers together, nothing changes. Okay? So if I do U1 to U1 plus some displacement d, and U2 to U2 plus the same displacement d, the energy doesn't change. Okay? So it means that T of U1, U2 must be a function only of U1 minus U2. So that's a nice simplification. It's a function of two variables turns into a function of one variable. This makes sense, you know. You can think it's a function of how far one layer is displaced from the other. Okay. Totally natural. Okay. And if we could actually stop here kind of and just try to say, well, I know what the tunneling matrix is if I have AA stacking, if I have AB stacking, if I have BA stacking, and just try to interpolate. We do a little bit better with symmetry arguments. Okay. I'm going to erase this now. Don't need it anymore. That's the first symmetry constraint. Second symmetry constraint is that if you translate just one layer by one lattice spacing, so this is a Bravais lattice vector of graphene, then the energy shouldn't change. Okay? Because then I just move every site on top of another site. All right. So it's not a carbon-carbon lattice spacing, it's a unit cell spacing. All right. Good. Okay. Now this actually has an effect. Basically, because it's a displacement, under such a displacement, we have that, so the displacement shifts the coordinate by x, and so under that displacement, let's say psi 1, shifts by e to the I k dot a. Okay. So this means if our energy is to be invariant, we need that T of U plus A. Why this? Because U is U, the argument of T is U1 minus U2. So if I shift U1 by A, the argument of U shifts by A. This has to compensate this. It has to be e to the minus I k dot A times T of U. Okay. Remember, this is a matrix. Double bar means matrix. So this is a kind of equation we're sort of familiar with in solid state physics. This is basically like a block requirement. Okay. So this tells you that T of U is a plane wave times a periodic function. Okay. So this implies that T of U, I'm often going to forget to write these things, but, is e to the minus I k dot U times a periodic function. We can write it in general as a sum of reciprocal lattice vectors q e to the I q dot u, where these are reciprocal lattice vectors for graphene. Okay, and each one can be multiplied by a t. TQ. All right. We don't know anything about the coefficients just from these arguments. All right. Now we'll do something that Bistreitzer and McDonald also did, which is this is in general an infinite series. That's way too complicated. Let's keep the smallest possible set of T's of Q's that could be consistent with symmetry. So it's nice to write it like this. Let's bring the e to the minus I k dot u into the sum. It's k minus q dot u, T of Q. Can you see this? Okay. Well, let's draw a little picture. Here's our Bravais lattice. Here's K. We'll just keep the vectors Q such that K minus Q all have the same length. They're all the ones that are related to K by simple lattice symmetries. All right, so there are 3 of them. I'm going to call the original K, K0, is 0 for original. There's another one, K1 here. This K1 is K plus this vector, which is a reciprocal lattice vector. Okay? And we'll call this one K2. All right? Make sense? So you learn when you study graphene, you know, that these 3 points are all equivalent by reciprocal lattice vectors. They're the same point in the one sum. Okay. So our approximation is going to be that it's kind of simple. There are just 3 terms, j equals 0 to 2. At this point, 3 arbitrary matrices that go in front of it, tj, is it plus or minus? Minus I kj dot r, dot u, excuse me. Yeah. Okay. Bigger. Okay. So far we just used translation symmetry, so there's a bunch of other symmetries. All right. We have to, when we talk about displacements, I have to define some reference configuration. So the reference configuration is just going to be AA graphene, so things are right on top of one another. All right. So we start with AA graphene. Looks like this. Okay, this is the top layer, and this is the bottom layer. They're both right on top of one another. All right. So that reference configuration has a lot of symmetries besides just translations. What I need here, remember which ones I need. Yeah, so one nice symmetry is reflection in this plane. Draw this line, we can reflect here. So this is y goes to minus y symmetry. That's a nice symmetry to consider because it doesn't change k to k prime. It keeps the values invariant. It changes the y component of momentum, but not the x, and since the k point is at the right-hand corner, it doesn't change, right? But it interchanges the A and the B sublattices. Remember, this is A and this is B in both layers, okay? Invariance under this means that, you know, psi goes to tau x psi. So in fact, turns out that we need that T0 here is tau x, T0, tau x, okay, because T appears between 2 psis. Make sense? Just like, you know, when you conjugate an operator by a symmetry, you have to conjugate it on both sides. So that's one constraint. Other important constraint is, so this is, I call this reflection in the y direction. Another important constraint is the combination of inversion or twofold rotation and time reversal. Why do I have to combine them? Well, if I do a twofold rotation, that takes k to minus k, and so it interchanges the 2 values. I need to do time reversal too to bring the values back, because I'm trying to make a model just for the k point valley. So the C2 operation, again, exchanges the 2 sublattices, and because time reversal complex conjugates, so this imposes actually that T0 is tau x, T0 star, tau x. Okay. Yep.
Could you remind me what the
Tau is this Pauli matrix that operates in the sublattice space. Okay, so tau z equals +1 is the A sublattice and -1 is the B sublattice. Tau plus takes you from the B sublattice to the A sublattice. Tau minus takes you from A to B. Okay, tau x interchanges A and B. That's why tau x appears here. Okay? Both places. Okay. Yeah. Okay. This might be a little heavy for the experimentalists, but if we look at this, this is actually pretty simple. We can solve that. How do we solve it? Well, you know, the most general, any general 4x4 matrix can be written as A plus B tau x plus C tau y plus D tau z. Okay. If we require that tau 0 is equal to tau x, tau 0, tau x anticommutes with tau y and tau z. So that forces these to be 0. And then this forces A and B to be real. Okay. So I'm going to write this as U plus W tau plus tau minus, where U and W are real. There's only one other symmetry I haven't used, which is rotations, threefold rotations. Threefold rotations are nice because, of course, if I rotate K0, I get K1. I rotate K1, I get K2. So these relate the different hopping matrices. So this actually tells you that Tj plus 1 is something like this, Tj. And I don't guarantee the signs here, but it's that's an operator that does a rotation in the sublattice space by 2 pi over 3. Okay. So this tells you you can just obtain the other two components of this hopping matrix, T1 and T2, from T0 just by this formula. Yeah.
The question, just to make it clear again, I mean, these T operators, coupling, they are not between sides of the same lattice. They are of the same layer, they're interlayer.
They're interlayer.
So
Yeah.
These are symmetries of the interlayer.
Of the combined system. But so you remember that we're keeping the displacement as a degree of freedom here. So if you start, so the description starts with this AA bilayer, which has all these symmetries, plus an arbitrary displacement field. So if I do, for example, this reflection, I get back the same original system plus a reflected displacement field. But it's still in the same framework, so I can still apply the symmetry constraints. Okay, so that's how this works. Right? That's true for any symmetry. So the result of this is actually pretty simple. We can obtain, you know, T1 and T2 from this. Basically, this just adds a phase to tau plus and tau minus. Okay, because tau plus and tau minus are like x plus iy and x minus iy. They just rotate in the xy plane. So the result is actually, for the full thing, is w tau plus zeta to the j plus tau minus zeta bar to the j. So this is a jth power of zeta. This is a general formula where zeta is e to the 2 pi I over 3. Okay. So if you dig around in Bistritz or McDonald, this formula mysteriously comes up, okay, out of these crazy sums over momenta and Poisson resummation. Okay, it's a miracle, but actually, now you can see it comes from rotational symmetry, basically. Okay. Good. All right. So now we did, I erased the logic. Okay, remember, oh, you know, here it is, the logic. First we do this in the R frame, now we transform to X. Okay. Transforming to X is actually pretty simple. We wrote, we have this, so we have H. Was this actually? This thing. Sum on J, e to the minus I kj dot u tj psi 1 plus, okay, plus our mission conjugate. Now again, I have to do the same series of manipulations that we did in the first part. I substitute for psi of r psi of x, and I make all the changes of variables. The difference is almost all the terms from the change of variables here are unimportant. We just need this term in the exponential, which I erased. Okay. Psi of r is psi of x e to the I k0. We need this. We need to use psi of r is psi of x e to the I k0 dot u. Okay. Plug that in here. Now we have to be careful of the layers. So for layer L, we should use the u of layer L. Okay, this is where the difference of displacements between the two layers come. All right. So here we got a e to the I. Yeah, this u. Let me be careful. This is u1 minus u2, right? Sorry, it's not very nice. There. Okay, remember very early on we determined it was a function of u1 minus u2. So this psi1 brings a factor of e to the I k0 dot u1. This brings a factor of e to the minus I k0 dot u2. Bless you. And so we get here, let me call it Tx of u1 minus u2, where Tx of u means actually sum over j, e to the minus I, kj minus k0, dot u tj. And these tj is what's in that formula, okay? Okay. So this is our H tunneling. Okay, does it make sense? I hope. All right. So now we can check this. It's a little bit formal, but let's just check if this works. Okay. So what? Yeah.
The index I pop up.
Is there an I? There shouldn't be an I. This? That's the imaginary I.
No. Yeah. Okay. Cool.
There. That's. I didn't erase something. Okay. So now let's do some checks. So the most obvious check is let's just take u equal to 0, so the two layers are not displaced. That should be AA stacking, all right? Well, we have this formula, okay? That means this tunneling matrix becomes u is 0, just sum on j of tj. And there's a very nice result. If you sum on j, zeta to the j, that's 0. You add the three roots of unity. These are complex numbers. If I think about zeta in the complex plane, this is zeta over here. Here's a unit circle. This is zeta. This point is zeta squared, which is zeta bar. Zeta bar means zeta complex conjugate. And this is zeta cubed is 1. You add these up, you get 0. Okay. And it's also true for the bar. So you add this thing, this sums to 0, this sums to 0, you just get 3u. Times the identity matrix. You know, if I wanted, this is a matrix, I should put an identity matrix here, if you want. Okay. So this is what we expected for AA graphing. We just have equal tunneling between every site, A to A and B to B. That's what that means, right? Same tunneling for every sublattice. And we see that the strength of the tunneling is 3u, so we should think about u as basically T prime AA over 3. All right? That's the strength that the tunneling would be for AA graphing. Now we can try u equals a displacement that would give me AB graphing, which we saw is something like 0A. I don't know if it's 0A or 0 minus A or something like that. Okay, remember, if we just translate, so what does this mean? U is the relative displacement of the two layers. I translate one layer up, I'm going to end up in this AB scenario where I have one site in the middle of the honeycomb. All right. Okay, well, now it's a little more complicated, okay? Here's my formula. I need to understand what kj dot k0 times dotted into 0a is. All right, okay, now you have to do some geometry. You know, k0 is along the x direction, so k0 dot 0a is just 0. All right. So this is just kj dot 0a. So it's just the a times the y component of the jth vector. Sorry?
I have a question.
Yep.
Okay, u0, then you write u equals ta prime a.
Oh, I'm sorry. Yeah. There's no vector on it. No, I'm sorry. I'm sorry. What's it? How about v? You want v? Let's call it v. V, 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 v. V, v, v. Now I got to make v everywhere. This is v. V. No, u is the relative displacement. V is just this number. V is some number here. V is just a number. I'm sorry. So these were just undetermined numbers. Okay. The symmetry argument told us everything about the tunneling matrix except these two numbers. They had, at this point, no significance. We're trying to discover their significance. They're not at all related to displacements. I'm sorry. That's screwed up. Oh, I feel so bad. Is it clear now? Terrible. Okay. That's a rookie mistake. All right. Good. Okay, so we discovered that V is actually the hopping strength. Okay. What about here? Okay, so this should be the AB bilayer. So you have to do a little geometry. You have to compute this. You know, for K0, it's 0. All right. So this is equal to 0. For j equals 0. For j equals 1, it turns out to equal 2 pi over 3. And for j equals 2, it turns out to equal minus 2 pi over 3. Okay, it's clear they're opposite because these have opposite ky values. Okay. So, you know, lo and behold, this factor is just some power of zeta. Okay. So, do it properly. We get that T of 0a is sum on j. This thing is actually zeta to the minus j times tj. So again, we can use this formula. Multiply everything here by zeta j. This becomes v times zeta j, which is, when you sum it gives 0. Here the zeta j's cancel. So, should I do it? All right, I'll do it. So this is sum on j. Just multiply that through. We have v zeta j times the identity plus w tau plus w tau minus zeta to the minus 2j. All right. And these two just sum to 0. And this becomes 3w tau plus. Okay. Which is exactly what it's supposed to be. Okay. This means you just hop from the A sublattice to the B sublattice. Okay. Symmetry works. It's beautiful. All right. It tells us what this mysterious W is. It tells you that W is the interlayer hopping when you have AB sublattice. Divide by 3 because it's funny factor of 3. Okay. So we had two unknown parameters that were just numbers. Now we know what they are. They're just interlayer hoppings. Okay. And basically 3 times interlayer hoppings. 1/3 of interlayer hoppings. I'm sorry. Okay. So these are not unknown. You know, we know what the strength of these interlayer hoppings are because people have done lots of experiments on bilayer graphene. And the expectation would be that T prime AA is approximately T prime AB, and both of them are around, 300 to 400 millivolts. Okay, that's a big energy. You know, you guys should know a millivolt is about 10 Kelvin. Theorists should know that. Experimentalists, I'm sure, know it, but the theorists should know it. That's a big energy, but it's still awfully small compared to T and the bandwidth, so all good. So these W and U should be of order 100 millivolts, more or less. Okay. Kind of people usually take a number, something like that, 110. I don't know. Okay. All right. So now we got it all. Got it all. We know everything. We can put it in and finally write this wonderful model. We go back and combine what we got from step 1, the geometrical transformation, and this hopping thing. And we get, I'm going to write the Hamiltonian density, this curly H. And let me write it out explicitly as the sum of 2 layer contributions. So from the first layer, we get minus IV tau dot gradient, and then we get minus V K dot d mu U1 psi 1. Okay, so this was this rotation bit that we kept. I've dropped everything else. You can keep it if you want. It's fine. Do the same thing for layer 2. And then we have to add the tunneling in. Bless you. Okay. So I claim this is a good approximate expression for bilayer with arbitrary strains U1 and U2 in the 2 layers. Okay. Modulo the things we dropped, but you could add them back if you want. And the nice thing about this is we can now specialize to the case. So U here is U1 minus U2. Okay, we can now specialize to the case where we just have rigid twists of the 2 layers and recover the Bistritzer-McDonald result. So this is already more general than what they have, okay? But I think simpler to obtain. So what do we want to do? We want to twist. Twist. Really, really twist. So good. Okay, so we make a small twist of layer 1. It's very simple. It's like this. So you take the cross product of the vector around the x-axis. All right. So this is just, if you want to write it in components, U1x is theta over 2 minus theta over 2y. And U1y is theta over 2x. Okay, so this is a clockwise twist by theta over 2 of the top layer. And then for the bottom layer, we're going to do the opposite twist. Okay, so that's all we need to do. Plug that thing into here. We're in business. All right. Pretty simple. Yep. Yeah, so that was immediately evident before this transforming to the X frame here, okay? I erased that, but that form, remember we said that T in the Lagrangian frame was a sum of exponentials of reciprocal lattice vectors. So that was the periodicity requirement. All right? I mean, in fact, this is a periodic function of u. Okay. I should say, sorry. So these things are just, you know, what are these vectors? Maybe that's helpful to draw them, right? Remember, this is k0, this is k1, this is k2. So k0 minus k0 is just 0. K1 minus k0 is this vector. And k2 minus k0 is this vector. Sorry. What am I doing? Yeah, that's right. This one. Okay. These are just two. They're all three of them are reciprocal lattice vectors, so it's periodic. Okay. Yeah. Good. Yep. All right. So now, all right. So we could look at these first terms. So k dot d mu u1. Well, k is just k along the x direction. So this is just d mu of u1x. All right. And we saw u1x is minus theta over 2y. So this is minus k theta over 2y hat. And k dot d mu u2 is just the opposite of it. It's k theta over 2y hat. Okay. So this makes sense because, you know, this is k0 is k. We make a small rotation by theta. We move this up along the y direction by this angle. Finish. 10 minutes. Okay. And this moves down, right? So these are just the shifts by rotation. What about here? Well, okay, so u1 minus u2 is just twice u1. It's theta over 2 z hat cross x. So if we take kj minus k0 dotted into u1 minus u2, this is theta over 2 kj minus k0 dot z hat cross x. So this is a triple product. We can use cyclicity of the triple product, okay, to write this as theta over 2x dotted into kj minus k0 cross z hat. So this is some wave vector. I call it capital QJ, I guess. I don't know what I call it. Capital QJ? Little QJ? Capital QJ, I think. Come on. Maybe a little QJ. Let's call it little QJ. Little QJ. Little QJ times x dot into x, where little QJ is just theta over 2 kj minus k0 cross z hat. Okay. Now, why did I call it small q? Because it's small, because it's proportional to theta. That's all. Oh, there's probably no 2, I'm sorry. The 2 cancels. All right? Yeah. Good. So this is a vector normal to these k vectors, all right? Well, I invite you to work out what they are, all right? Of course, Q0 is 0, and they're just perpendicular to these and small. So what's the significance of these? These turn out to be, so there's 0, Q1, and Q2. You can actually check. Okay, last time I told you what the unit cell size of the Moire pattern was, and that if you translate in the vertical direction by that unit cell size, you get to another unit cell. That told you the real space periodicity of the Moire lattice. These are exactly the reciprocal lattice vectors of the Moire lattice. Okay, the unit cell got big, the reciprocal lattice vectors got small. That's exactly what these are. So you put these things in. we get that H twisted. This is H twisted, I guess. Is psi1 dagger minus IV tau dot gradient. And there's this thing, what do I get here? Here we go. Plus k theta over 2. Tau y. Psi2 dagger minus IV tau dot gradient minus k theta over 2 tau y. And then I have the tunneling term, which is minus sum on j. I don't know if I have the sign right, but something like e to the minus I qj dot x psi, whatever it is psi 1? Yeah, okay. Anyway, I don't know what this is. tj psi 2 plus remission conjugate. And it's possible I switch the 1 and 2 somewhere, okay? Something like this. So this is just this actually is the Bistreitzer-McDonald model. We can write it in a one particle Hamiltonian form. H1 particle psi, where yep.
Where's the theta? I mean, it's a theta missing. Theta on the left-hand side. I mean, qj is equal to theta kj minus k naught
Yeah,
plus z.
yeah.
And at the end, the theta is no longer there?
Yeah, I define it to be this thing that's dotted into x. So this is just qj dotted into x,
Yeah.
okay?
And you say that
And that's what's in the exponential here, right? So we took, I'm just taking this exponential, it's this dotted into this, okay? That's so, again, to just do the counting is kind of easy. So the displacements are small for a small angle. Everything's proportional to theta. So the smallness is preserved here, the q is proportional to theta.
Moire lattice. No, so theta times this guy is that the reciprocal lattice vector.
Yeah, so what you learn is kind of the reciprocal lattice vectors of the Moire lattice are theta times the reciprocal lattice of the real lattice rotated by 90 degrees. Okay? And you can check that that's correct from this sketch I drew before, right? And this, if we want to write this one particle Hamiltonian in the form that I like to do, okay? Let's think about this thing. This is a 4x4 matrix. It's a differential operator, but it's also a 4x4 matrix. Why? Because each layer is described by a Dirac spinner, 2 components for the 2 sublattices, and we have 2 layers. However, this is really, I should write some 4x4 matrix, and I always prefer to do this by writing lots of Pauli matrices to confound you, all right? So we have tau for sublattice, and I'm going to introduce another one, gamma for layer, all right? So when I go from one layer to the other, that's going to be like gamma plus. When I have something that's the same in both layers, it'll be gamma independent. So the Dirac term is the same in both layers. So that's just minus I v tau dot gradient. And then we have this thing, which is opposite for the 2 layers. So it's proportional to gamma z. Tau y gamma z, and I'm going to write it like this. It's, oh, there was a v. I lost a v somewhere. I'm sorry. Be a v here. There was a v here. So I'm defining what people usually do in these Moire business. They define a It's V Fermi. It's the Fermi velocity. Oh my God. All right. Yeah, so k theta here, you can read off here is I guess, k times theta over 2. All right. I believe that's right. Oh, no, it's just k times theta because I kept a factor of 2. All right, so this is actually how much the two Dirac points rotate apart from one another. So in that picture of the zone, the Dirac point in one layer moves to here, the Dirac point in the other layer moves to here. This is Vk theta, Vf k theta. All right. And then we have this tunneling operator, which looks like minus sum over j, e to the minus I, oops, qj dot x tj plus Hermitian conjugate. Oh, and it needs a gamma plus Hermitian conjugate. Okay. So there's a nice one particle Hamiltonian. And actually it's periodic because QJs are the reciprocal lattice of the vectors of the Moire lattice. So this Hamiltonian has the periodicity of the Moire lattice. So it's ready for Bloch's theorem. Okay. You can put it on a computer, look for solutions that are plane waves times a periodic function, and just solve it. Okay. All right. I just want to wrap up by mentioning one simple thing. Talk about energy scales. Okay. So remember here, Tj, I guess I erased it, is what did I, V? V, yeah. V plus W zeta to the j tau plus zeta bar to the j tau minus. Okay. So if you, it's nice to kind of look at dimensionless variables here. Okay, so we should apply Bloch's theorem to this. That means we solve it for solutions that are plane wave times a periodic function with the period of the Brillouin zone, period of the real space unit cell. Okay. So there's a natural length scale. Is the length of the Moire pattern, which is, like proportional to 1 over k theta. Okay. So if we can kind of non-dimensionalize this equation, we can divide our one particle Hamiltonian by the natural energy scale, which is Vf times k theta. Okay, so k theta is a momentum which is of order the width of the Brillouin zone of the Moire pattern. So this should be familiar. Remember that yesterday we showed this little cartoon where we just shifted 2 Dirac cones by plus or minus k theta. That's the energy difference between the 2 Dirac cones. Okay. So that's the sort of one natural energy scale. The other natural energy scale is this tunneling strength, which are these parameters actually W and U. And if we measure everything in lengths like this, so we go to new coordinates, we let k theta x go to x, so we measure, now x is dimensionless coordinates, so x equals 1 is like the length of the unit cell. Okay. And then you'll find that this Hamiltonian is just minus I tau dot gradient, tau dot gradient plus a half tau y gamma z minus, and we can write it like this. Red. K theta sum over j e to the minus I qj tilde dot x tj bar gamma plus Hermitian conjugate where Qj tilde are like Qj divided by k theta, so they're dimensionless. They're just numbers. And Tj bar, I've pulled out tunneling strength W. So Tj bar is just V over W plus tau plus zeta to the J plus tau minus zeta bar to the J. Okay. So this is the Hamiltonian whose corresponding Schrodinger equation gives the Bloch states, whose energies are phrased in units of VFK theta and lengths in units of the unit cell. So everything is as dimensionless as we can make it, and we can see there are basically two dimensionless parameters. There's one important one, which I indicated here. W over VK theta, that's the really important dimensionless parameter. Okay, it measures kind of how strong is the tunneling, how much is this, if this were actually small, then basically the tunneling is very weak and we have free electron states. There's just independent electrons in both layers. As we turn this up, the two layers are hybridizing a lot. So this, if W over VK theta is small, if you regard this as a Bloch problem, you know, this is the periodic term, and these are just gradient terms. These are just momentum terms. So this is like kinetic and potential energy. The potential energy is weak, so it's nearly free electron approximation. When this gets big, it's a very strong potential. It reveals, you know, that when W over VK theta is much bigger than 1, this is highly renormalized bands. And I'll remind you that this is W over VK theta. So smaller theta is, the bigger this thing gets. So that happens at very small angles. The renormalizations of bands get huge. So all the neat physics is at very small angles. The other small parameter, other dimensionless parameter is V over W, but these are both just interlayer tunnelings between carbons. They're basically the same. So physical value of V over W should be of order 1. Okay, a little bit less than 1, probably. Because and this is coming from this, somebody asked, I don't remember, about the relaxation. How do the layers adjust? Do they move vertically? Does their layer separation change? So, you know, the AB is the structural ground state. So they bind more strongly for AB binding. So actually the tunneling is a little stronger in AB than for AA. So that's an important effect, actually. And that makes this a little bit less than 1, but not small. So I think I've gone over. I should stop. It took me, I think, a bit longer than I wanted, but all right, we'll have a lot of fun stuff to do next time. So no more band theory. It'll just be serious. So. Thank you. Questions? More? Yep.